Hello everybody, my name is Timothy Warder. Welcome back to my channel. If you saw my last video, it was, this is going to be a follow-up to that video, although if you're my TA, so you only need to look at this video. So this is just going to go over an updated version of the Matlab, VREP, A-star, and simulation. I added a few new nodules in here to make things hopefully a little bit more robust. So let's go ahead and jump into it. I'm using Matlab 2018B to simulate my environment using A-star to do my path planning. And then I'm using VREP with the University of Maryland at College Park's RRL map, which is the Robotic Research Laboratory, and a little Turbobot 2 down over here. So let's go ahead and jump into our MATLAB here. As we can see, we're locked into A-star. And then we'll go ahead and run this program. And then just like last time, we have the option to do this in a point robot or a regular robot presentation, or rigid robot. If we do the point robot, it's going to be a little bit faster. And once we enter into our graphics simulation environment, we can actually see and explain what's going on. So we'll go ahead and hit yes. A new addition to my code is that we now have a maximum and minimum speed of 10 RPMs and 100 RPMs. So if we end up going outside that, it's just going to reset us to a default of 10 and 40. Instead of showing that off, we'll go ahead and show that off. Let's just say we do 9 and 101 RPMs. Look at that. Speed is outside the ranges of 10 and 100, so we'll go ahead and set the speeds to a default. We'll go ahead and leave our robot position at 1-1, just like we did last time, and our end goal position at 9-5, like we did last time as well. But as we can see, we can enter in different values, and we'll end up using those. But we are going to go ahead and stick with our defaults. Now, we got a lock of 0, which means that our robot and our end goal are not in conflict with our objects, especially since they've been enlarged. If we look at this specifically, we can see that we have a dot right here. This represents our robot. And our goal point over here, that is also surrounded by a little bit bigger of a box. This is to say, if we get to this location, we have successfully made it. It should be I think it's about half a meter in distance, in radius. And then all of our objects have been enlarged, just like last time. If we didn't do the point robot, all these objects would be smaller, and our robot would be the size of the robot in the simulation. So let's go ahead and enter our main loop. So now is searching for our end goal by traveling to each different node using the A-star program. And boom, in 10 seconds we were actually able to find our location. We can do a live plot of it. We're not going to, since that ends up being a little bit of a time bit. And then in a sec it should show up all the blue nodes that we visited, and as we can see, we are now following our robot from its optimal path to the goal. Cool. So once we have that done, we'll jump into our VREP API, and we'll go over some of the new bits that we added. So we have our starting the remote service. We'll shut down that remote service to make sure that we don't have anything else going on. Double check to make sure that we're connected. We'll stop any simulations in order to give ourselves the ability to restart it. Pause it for a second to make sure that the command went through, and then start the simulation again. Next, we'll end up grabbing all of our handles and our float signals. Our float signal here is the Turtlebot simulation. Because Matlab and VREP run off of 2 different simulation times, we're going to want to make sure that we grab the simulation time in VREP. And then one of the new things that we brought in is fast Hokuyo, which a friend of mine in the class was actually let me onto this little bit. And the difference between the Turtlebot 2 and fast Hokuyo is that the Turtlebot 2 deals in Euler angles, so we weren't actually able to get a good orientation. But Fast Hokuyo, where are you? Right here. Fast Hokuyo deals in absolute angles. So with a little bit of modification, we are actually able to utilize the orientation of our robot to give ourselves a partially closed loop. We are still using an open loop for the most part to get our position. This is because if we end up using a fully closed loop by getting orientation and our position, if we end up being just slightly off, we're going to start building up errors as we get to a little further in our timetable. And if we end up getting so far off that we don't get to that position, then even if we set like a parameter saying, hey, if we're plus or minus 1 within this position, we may end up not being in that position due to the pileup of errors, and it'll just crash into everything. So we're still using a semi-open loop in order to get us there, but we do correct for the orientation just to make sure that we're getting a little closer. We then bring in our speed stack, and we get our X and Y positions. Even though we don't use those, it's kind of good to know that we have them. We get our angle that we want to operate at, and then our left speed and right speed. And then we go ahead and grab our simulation time. We multiply it by our scaling factor once again, which just seems like it's an issue with Matlab and VREP in terms of using the while loop and their clocks. We set our target velocity for the left and right wheels, and then we go ahead and grab our time. And then if that simulation time is less than our simulation step time, we just continue. And then the new part of the code is that we will actually correct our orientation. So if our simulation angle is greater than 0, then we will move our robot 0.1 left and 0.1 right in order to get it into the correct angle if it's a little further, if it's a little less than our simulation angle. And if it's greater than our simulation angle, then we'll go ahead and do the opposite. So this bot will end up doing a turn right in place to make sure that we don't end up moving too far off. And then we'll pause and move on to the next step. So let's go ahead and run this code. We have 53 steps. Here are all of our speeds that we're going to be operating at. And then this is our speed stack. And we'll go ahead and launch into this. As we can see, we are correcting for our angle. And we're going to go ahead and move on with this, and hopefully by the time we end our simulation on our 53rd step, we will get over here. Granted, this is a little bit of a timely bit again, so we'll end up just go ahead and leave it at this. Now if we want to double check to see that our path is going well, we can look at this. Boom. Now we're supposed to get at 9.5. So with our area, we're supposed to get about 8.5 by, let's see, 5.5 I think is what our nominal position would be, with according to where our robot should be. So it looks like we're just about a meter off or so, which isn't too bad. So thank you for watching. As always, I'll have information about this project down in the description below, and you have a wonderful day.